phase back up. Okay, so on Friday and Thursday, we were talking about friction and in our little friction lab. And one of the things we saw in our lab was that it seemed that as we added more and more mass to an object, the amount of friction went up. And that friction, whenever we were graphing it, there was some like force of friction and it was a time. And that little hand was like, it was pulling, and then the block started to move and it was like, whoop, and then it went like this. There was like this gap right here. And we called the top of this here, this was like a static friction. It was the amount of friction there was before the pull. And then this was a kinetic friction, which was the amount of friction or the force of friction, that was occurring while the block was sliding along. So we saw that the static friction was bigger than the kinetic friction. And something else we saw, like I said, was it seemed that as we added more and more mass to our block, there was more and more friction. This graph kind of like stayed like this. It just, it went up higher and had that. So there's just more overall friction as the mass increased. We also saw that depending on the surface we picked, the amount of friction changed as well. In part 3 of the lab, we saw that, if we had something like rubber on cement, there was a lot of friction there, but something like rubber on ice, there wasn't very much friction at all. It moved very easily. So it seems like the types of surfaces, the two surfaces we bring together, influence the amount of friction, as well as this mass. And one of the things we looked for in the lab was this idea of a coefficient of friction. And we solved that by saying the coefficient, which we'll just write as the coefficient right now. We'll have a variable for that in a moment. But we saw that was just equal to the force of friction divided by some amount of weight. And we specifically used the kinetic friction in this lab divided by the weight. And that was a pretty good way of actually solving for the amount of friction, or for the coefficient of friction, that is, between two surfaces. But we're going to see today that this equation here, the coefficient equals the friction divided by the weight. While it's good, it's not perfect. There's a few things in this equation that are a little off, specifically this weight. We'll talk about it. And in doing so, we're going to get a true equation for our friction that we are going to use this year. And we're actually going to take a look at an example problem of how we can apply this friction to our F equals ma type of problems here. So if we jump back over to the notes, we're actually going to see that a true equation for friction is that friction is fuN. And this is F friction, and we tend to write that as a scroll F. That's going to be equal to two variables multiplied together. The first variable is the variable mu, said the same way as the Pokemon, number 151. That is a mu right there. It is a Greek letter. And this right here, this is the coefficient of friction. That was what you were finding in the lab whenever you're doing your calculation. We can take that coefficient of friction and multiply it by big N. This is the normal force. It's not a weight. It's a normal force, which we're going to talk about why we use the normal instead of a weight. But it is the force of contact between the two surfaces. So while mu is the types of surfaces you have, rubber, concrete, bark, carpeted floors, hardwood floors, whatever, that is just your two surfaces in contact. And the force of contact is your normal force, okay? That is what defines friction. And because of this, we can commonly say that friction is fuN, because you spell fuN, F-U-N, and you have here F mu N, okay? So this is what defines friction, a type of surface, and then the normal force, or that force of contact. When we were brainstorming, we thought of a few other things that could influence friction, and there are a few other things that do, but at a very, very small amount, so we actually don't care about them. One of them is the surface area. If you had two boxes, and let's look at them from like a top-down view. So this is a top-down view, okay? And one box is rather small, and it has a mass of, let's say, 10 kilograms. And then there's another mass, or another box, much larger. Its mass is still 10 kilograms, but it has a much larger area. Technically, if we were to like slide these along the floor, technically the box with a larger area would have more friction, but it is by a very slim margin. It's like not even a full Newton. generally speaking, unless you're doing something that you need extremely precise measurements and data, you're building sports cars, you are sending someone to the moon, you really don't care about this surface area. It's really not something we need to worry about this year, so we're ignoring it. Notice how an area doesn't pop up into the fuN equation. It's just types of surfaces, mu, and then the normal force. So while surface area is a thing, doesn't really matter for us. And the other thing that someone mentioned was the speed. If an object is moving faster, the force of friction between surfaces will actually go down, but it goes down by a very small amount, so nobody cares. Okay, technically it's there, but unless you're doing something where you once again care about very, very subtle differences, it doesn't matter at all. Okay, so generally speaking, we just say F equals mu n, and that's the only thing that matters. Now in our lab, we also saw that there were two types of friction. And, if we go back over here and take a look at our diagram, we saw that we peaked at a point up here on the graph, and that was our static friction. There's two types of friction here, or two types of coefficients of friction. There's a static friction and a kinetic friction, which we can write as Fs and Fk for static, not moving, and kinetic, moving. This also gives us a coefficient of static friction and a coefficient of kinetic friction. The coefficient of static friction will be larger than the coefficient of kinetic friction. That maximum is going to be that way because it's harder to get an object moving and overcoming that initial friction than it is to keep it moving. And that's just because the bonds as an object is sitting in a spot, the kind of molecules kind of like teeth together a little bit more, and you have to pull them out versus whenever an object's moving, they're just kind of going across a bumpy road. So our static friction will be greater than our kinetic friction. We saw that in our lab with those drop-off points, and that's why here, okay? Traditionally, we are just going to, for our type of problems, we're pretty much going to just look at the kinetic friction for the most part. But if you had a static friction, it would be larger than the kinetic, okay? Our static friction is normally just equal to whatever applied force is acting on our object until it begins to move. So this static friction kind of goes up and up and up, and then as soon as it moves, we get this value of the kinetic. Okay, and that's what we saw in our graph over here anyways. This static friction went up and up and up and up and up and up and up. It hit a peak at some point, and then it drops off, and we just have the kinetic left. Okay, so that's what we have just in terms of our ideas of friction and what's going on there. So if we're talking about friction then, let's spend a little moment of answering the question, why do we care about the normal force in friction rather than the weight? Because in the lab, we were looking at the weight then. So why do we look at the normal force instead of the weight? Well, let's think about this for a second. When we were doing the lab, there was like a table or a bench or something, and the object was sitting flat on it. And if the object's sitting there here on Earth, we know that this object has a weight pulling down on it, and that weight is mg, mass times the acceleration due to gravity. Well, this object was not falling through the table, so something had to be supporting it, so pushing back up on the object. So there's a force pushing back up here, and since that force is the perpendicular force to the table, we call that the normal force. Now, because the object isn't sinking into the table, and it's also not flying away, it's not like shooting off into space, that means the normal force and the weight have to be equal, because this object isn't accelerating up or down. So this normal force on a flat surface better equal the weight. And since we know weight equals mg, in our lab, it didn't really matter if we used the weight or if we called it the normal, they would have been the same, okay? Now, another really interesting thing on why we use the normal force instead of the weight is the following. Imagine for a second, we have a wall. There are plenty of walls around me. If you take an object, like, I don't know, this Bucky coaster, and you put it on the wall. If you let go of it, it'll just fall. Well, why does it fall? Well, we know why it falls. It's because it's being pulled down. What's pulling it down? Gravity. Gravity gives it a weight. Okay, well, before when we had a weight, we had a normal, and the normal prevented it from falling. But this time we don't have a weight. We don't have a normal, excuse me. We have a weight, but no normal. So how do you actually hold something against a wall? Well, when you hold it against a wall, you kind of push it into the wall, right? Like my finger's pushing Bucky's face into the wall here, and because of that, it's staying there. And if you take any object and you hold it up to the wall, like try it, like you have to push the object into the wall in order to get it to stay. Well, why does it stay whenever you push it into the wall? Well, that's an easy one. When you push it into the wall, here's your push on the object. When you push the object into the wall pushes the object back. And since that's perpendicular, this push back from the wall, that is the normal force. So when you push into the wall pushes back, it generates a normal force. And when you generate a normal force, that normal force will generate a friction, because friction is fun. When you have a normal force, you can have friction. If you're not pushing into the wall, you just set Bucky there for a second, look away, he falls, he's gone. It's out of here. But when you push him in there, you generate a normal force, and that normal force is what we need. And we've actually seen this, or maybe you've experienced this on some certain carnival rides. There's a classic carnival ride. It goes by a million different names. Some call it like a roundup, some call it like a death circle. But essentially, whenever you're on this ride, you're just standing there on the floor, and this ride starts spinning around. And what soon happens as it spins faster and faster and faster is you become pushed into the wall due to the spinning nature. We'll actually talk about the centripetal force and what's going on later on in the year. But you get pushed into the wall, which means the wall is pushing you back. And when the wall's pushing you back, because you're wearing clothes and the wall has some surface, there's a coefficient of friction between you. And since the wall is pushing back with a normal force, there's a friction, which means that when they drop the floor out on this ride, you stay up on the wall because your friction is holding you up as the weight is pulling you down. And that happens because when you're in the circle, you're being pushed into the wall and the wall is pushing back on you. So the floor is down here. Like look at these feet, like feet, floor, floor, floor. They're a solid like 2 feet off the ground here because they just dropped the floor out from underneath them. But they're staying up due to this normal force and the force of friction holding them up. So you need a normal force for friction. If you don't have that normal force, then you have no friction. And in this case, they would fall, but they don't. They stay up, which is kind of a wild thing when you're looking at something like that. I've always wanted to go on one of these rides, but Mother always said that they were dangerous. They're not dangerous, Mother. They're just rides. So anyways, when we go back here, that gives us a better idea of why we look at the surfaces and the normal force. So let's take a look at a practice problem here. This problem is going to take a look at not only friction, but F equals ma, setting up our free body diagrams, and taking care of all of the math that goes involved with it. So let's take a look at this problem here. It's kind of hard to read it, but right here in the blue box, it says that the coefficient of kinetic friction is 0.2. So let's just write that. UK equals 0.2. And this is a unitless quantity. Technically speaking, the coefficient of frictions are newtons per newtons. And that's because whenever you graph them, if you graph this equation, if you graph friction and the normal force, what ends up happening here is you get some sort of graph. And the slope of this graph is the coefficient of friction. And since this is newtons and newtons, those are our units, newtons per newtons, which kind of cancel out. So most of the time, nobody writes it because they do cancel out there, but they're technically there. So if our coefficient of kinetic friction is 0.2, we would like to know what is the magnitude of the tension force in the rope. So we're looking for this tension force right here. And we know a few other things about this problem. We know the mass of the block is 1.6 kilograms, and we know it's accelerating to the right at a positive 2.2 meters per second squared, which is implying that in this problem, the right is going to be positive and the get is going to be negative. Okay, so we're just looking for what is the tension in that rope. Get given that there's some friction on the ground and the acceleration of mass. So if we draw our free body diagram, always the most important thing to do, make grandpappy bots are happy. There's our block. It has a tension acting on it. There is a friction acting the other way. And this block has a weight acting down equal to mg. And to counter that weight, it has a normal force acting up, which on this flat surface equals the weight, which equals mg. So if we wanted to kind of go through and solve this out, let's write our F equals ma equation. Remember, it's the sum of the forces equals ma. And when we do this, we only care about the forces that are acting in the directions of the acceleration. The x forces and the y forces are independent. So in this problem, we're really caring about these forces right here. Yes, the normal force is going to give us some friction, but in terms of what is that tension, that is acting to the right. So we care about our left and right, or our x direction forces. So if we set up our F equals ma in the x direction, this will be a positive tension, because that's going in the positive direction, plus a negative friction, so minus F. And then this will equal a mass times acceleration. There's only two forces acting left and right, so I have two forces on the left side of my equation. If we want to put in some numbers here, we can. We can say that the mass here was 1.6 kilograms. The acceleration was a positive 2.2 meters per second squared. And we're looking for the tension, so there's T. And then we have a minus friction. Well, remember, we know friction. Friction, if we recall, is fuN. So we know this friction is going to be mu n, and we know in this case on a flat ground, we know the normal force is going to be equal to the weight, which is equal to mg. So we can really say here that friction is mu mass times gravity. All of that is friction. And that means when we plug everything in, mu is 0.2, the mass is 1.6, and gravity is 9.8. And we want that 9.8 to be positive. Remember, we always use g as a positive 9.8, and then we look at our direction, positive or negative, which we actually have here to designate what's actually going on with the forces. So looking at this, we have a bunch of numbers. We can solve for the tension now. We just need to multiply some things together, then play some algebra. So we've got tension minus, and then let's figure out what this number is. That's 0.2 times 1.6 times 9.8. It's 3.14. Ooh, it's like pi. I love pi. And that equals, let's see, 1.6 times 2.2. And that's going to be 3.52. And these are all newtons here because our tension needs to be in newtons in the end. It's a force. And let's see, if we just add the 3.14 newtons over, whoosh, we'll find that tension equals the number of physics, 6.66 newtons. And that's our answer right there, okay? We solved for the unknown tension in this problem. It was a simple F equals ma setup. We had to recognize that friction was fuN and that we needed to find that value of friction. We did so by saying, look, we know the coefficient of kinetic friction is 0.2. We know what the normal force is. It's the weight, which is mass and gravity in this case. And then we were just able to plug in values and kind of solve things out mathematically. So nothing too crazy here, just what's kind of going on in the problem. If you had a problem that wasn't on flat ground, things change a little bit, okay? And the reason why things change is when we're on flat ground, the weight is acting straight down and the normal force is straight up. So everything in terms of the normal and the weight will be the same. But if you start going on an inclined plane, your normal force is going to be pointing perpendicular to the surface and the weight is going to go straight down, which is going to mean that the normal force is actually going to decrease. And at some point when you tip, your normal force will be so small that the friction will go down, and then you'll actually start to slide down your inclined plane or your ramp. So that's something to think about. We're not going to take a look at that right now. It's a slightly different problem, an inclined plane or a ramp, but it is something to recognize that if you're on a slope or an extreme slope, a vertical wall, that normal force may have to be found in a slightly different way, either with some trigonometry, sine, cosine, tangent, or looking at some centripetal motion, which is much later in this course. But this is a pretty straightforward problem. In this unit, we are going to stick to just things going left, right, up, and down like we have here. And that means this is finished.